the number theoretic transform. It's one of the critical parts of the Fry protocol, which is sort of at the heart of Stark's. So, what is the number theoretic transform? So conveniently, a few weeks before I was slated to give this presentation, I saw that the YouTube channel Veritasium had actually made a video on the fast Fourier transform, which is very related to the number theoretic transform. The Fourier transform in general is, you can think of it as a way of decomposing a function or a signal down into sort of component parts. In the case of the Fourier transform, the traditional Fourier transform, those are sort of these sine waves that you can see here. And it's something that's useful across many domains of engineering, signal processing. It's really a sort of very broadly useful mathematical idea, and it comes up in Stark's as well. And so what we'll learn today is sort of more about the specific version of the Fourier transform that is used in RISC Zero. And that is the number theoretic transform. So the Veritasium video also mentions briefly the so-called discrete Fourier transform, which is the idea that, if you're working on a computer, computers are sort of these digital machines that take in discrete data, discrete chunks of data. And so instead of a continuous signal, a computer is only going to see, a bunch of samples out of that data. And so the discrete Fourier transform is an algorithm that, can process a signal in that form and break it down into a bunch of constituent sine waves. The number theoretic transform is sort of a modified version of the discrete Fourier transform, but with two big distinctions. And the first is that, rather than a continuous signal, right, a sort of an amplitude that's a real number, the number theoretic transform works more over groups and finite fields. So if you came to the study club a couple of weeks ago, Paul introduced you to finite fields. And so that's the first major difference between the number theoretic transform and the discrete Fourier transform. The other sort of major distinction is that the concept of sine waves or cosine waves gets replaced by polynomials. You have a composition of sine waves, or you can have an addition of a bunch of polynomials. And it turns out that polynomials are the right sort of analog for a sine wave when you're talking about finite fields. And of course, polynomials are very important for zero-knowledge proof systems in general. And so I imagine some of you have come to the talks on previous weeks on these, but Paul has some nice YouTube playlists that sort of go over these things if you want to go over those. So what is the main goal of the number theoretic transform? And it's basically to do with the difference between so-called coefficient form and evaluation form of polynomials. So to produce a Stark, right, a computer has to have a very large polynomial in its memory. Basically, it's a polynomial with a lot of components. And there's basically two ways to write down a polynomial. One way is the more traditional way that you're probably familiar with. You write it down in coefficient form. So I can say I have a polynomial p of x, and that's a3x cubed plus a2x squared plus a1x plus a0, right? This is a degree 3 polynomial because 3 is the exponent here. And you can see that there are basically 4 pieces of information that are needed to convey this polynomial, right? We need a3, a2, a1, and a0. So if those 4 numbers, a3, a2, a1, a0, are written down in your computer's memory, then you know everything you need to know about the polynomial. The other way you could write down a polynomial is in evaluation form. And this is just to say that you can evaluate a polynomial at several points, right? A polynomial is a function. You can give it a number and it spits out another number, or you can give it a finite field element and it will spit back out another finite field element. And if you take 4 different locations and you evaluate the polynomial at those locations, then that's essentially as good as giving you the polynomial coefficients, because as we'll see, there are ways of going back and forth between these two things. And this is really important for the sort of Stark software, because it turns out that the person who's producing a Stark proof is actually going to have to do operations that involve both of these forms. There will be a list of evaluations, and the prover is going to have to publish some of those, and then there will be a coefficient form that the prover will transform it back into to do some sort of arithmetic operations on these polynomials to sort of reduce them. And so basically it's very critical that we be able to pass between the coefficient form and the evaluation form, that we should be able to take a coefficient form polynomial and transform it into an evaluation form. And also, if we have an evaluation form, if we have a bunch of different evaluations, we should be able to find the coefficients back from those evaluations. And so we need an efficient way of going basically back and forth between the two versions. I guess I'll stop, and I'll just make sure that ask if anyone has any questions, assess if anyone's sort of confused by anything or has any sort of thing they want to resolve before I move on.
Could you, this obviously we're operating over finite fields in this context. We want to use polynomials as the bases. Could you also use polynomial bases in non-finite field contexts, like over the real numbers?
Yeah, sure. So I guess what we're going to see here is that there's a transformation between evaluation form and coefficient form, and that's basically there's 4 variables and 4 unknowns. At least in this case, it could be more. But I don't see any reason why you couldn't do it using real numbers instead. It would just be, you would just be using the mathematics of the real numbers or some other field. It doesn't necessarily have to be a finite field. Although it does have to be a system of numbers in which you can divide. That actually is important. So it does have to be a field rather than a ring, if you know the mathematical difference between those two things.
Mm-hmm. That's helpful.
Just ask, so you have these coefficient and evaluation form. Does it mean that it's possible to evaluate the polynomial without knowing the coefficients, or not using the coefficient directly?
Well, so it should be possible to evaluate the polynomial at any point given the coefficients. I guess you could say that you do that directly by just sort of multiplying things out, and that's something that I'll show later. But perhaps something that I should emphasize is that the evaluation form is not just a single evaluation of the polynomial, but multiple different evaluations, right? If I just give you a single number, a single point at which a particular polynomial is evaluated, that's not enough to tell you the whole polynomial, because there might be many polynomials that pass through that one point. So you actually sort of need quite a bit of information, and there's sort of a distinction between doing the computation directly and doing it in a way that sort of is the sort of more number theoretic transform way, which is a bit more indirect, but actually gives you a lot of data all at once.
think the question, if I understood correctly, was if you just start with the evaluation form, can you evaluate at points that are not your x0, x1, x2, x3? Not if you start with the evaluation form.
Ah, that's okay. I understand. Yeah, that's a good question. Yeah, I'm not sure if there's a real direct way of doing that, but I mean, so one way that you could do it is if you had an evaluation form and you wanted to evaluate at some place that was not one of the points at which you had evaluated, you could take your evaluation form, and if you had a way of changing that into coefficient form, you could go into coefficient form, and then maybe you could, once you had it in coefficient form, you could then evaluate it at the point you wanted by, multiplying things out.
So I actually have some more context on this because I was randomly reading about this earlier. Basically, this is a big deal in the snark world right now, where they want to try to eliminate NTT from snark generation computations. And there's an evaluation form called the barycentric evaluation, which does indeed allow you to evaluate a polynomial at a different point without going through coefficient form first. And it is better under very under niche circumstances. Here's actually I just posted in the chat a link to an article by Vitalik on this topic that also links to a paper that has more information as well.
Yeah, Vitalik's articles are always great. Okay, great. Thanks for that. Something I think I didn't know, so I'll probably read that article later. Okay, maybe I should move on and talk about how we can go from coefficient form to evaluation form. So, starting with some polynomial, we would like to evaluate it at 4 different points. And perhaps we can start with a nice concrete example using the finite field F5. So this is the finite field that has 5 elements. You can think of it basically as the clock arithmetic or the modular arithmetic that Paul presented a few weeks ago. Whenever you get a number, you take the remainder when you dividing by 5, and that gets you your new number. So let's choose some random, basically, coefficients here. I've sort of chosen them arbitrarily. We have the polynomial 3x cubed plus 4x squared plus 4x plus 1. And let's say that we want to evaluate it at these 4 points, point 1, 2, 3, and 4. So one way we could do this, as I was sort of alluding to, was brute force, right? So, we can evaluate P1 by just sort of multiplying things out, right? We have 1 cubed, 2 cubed, 1 squared, 1. All of those are equal to 1. And so if we add all these up, we get 12, which is equal to 2 mod 5. And so that would tell us B0 directly. And then we could do the same thing for evaluating at 2. We can do 2 cubed, 2 squared, 2. We can multiply all of these numbers together, and you can use a calculator to check my math if you want. This comes out to 49, which is equal to 4 mod 5. And we can do the same thing with 3, and it comes out to 0 mod 5. And we can do the same thing with 4, and it comes out to 3 mod 5. But the sort of vaguely disappointing thing about doing things this way is that it takes actually a lot more time than you would want to. And the reason why this is sort of a very slow algorithm for computing this essentially has to do with the fact that we're doing a lot of different multiplication operations here, right? So for each and every one of these evaluation points, there are 4 different numbers to raise to a power, 4 different multiplications to do, and there's 4 different evaluation points. We're doing at least 16 multiplications right there. It's basically the square of the number of coefficients that we started with. And that's bad because, it might be possible for this polynomial because there's only 4 elements here, but for the sort of polynomials that we're dealing with when we run a Stark protocol, those can be very long, very high degree polynomials indeed. They can be, almost as long as the sort of the execution trace of whatever program you're trying to verify. So doing this sort of n squared quadratic, all of this work, this is not the fastest way of doing things, and we sort of want to look for a better way. But before we look for a better way, maybe it's helpful to just sort of realize the structure of the problem as it already exists. So let me first point out that this process of multiplication can actually be viewed as a matrix equation, or an equation in linear algebra, if you're familiar with that. So what you can see here is a matrix multiplied by a vector, and that gives us another vector. And this matrix here is meant to represent the coefficients that we see in this set of four equations here. Right, so we have ones all down the side here. We have 1, 2, 3, 4. We have 1 squared, 2 squared, 3 squared, and 4 squared. And we have 1 cubed, 2 cubed, 3 cubed, and 4 cubed. And so we basically make a 4x4 matrix out of those numbers. And then if we multiply by this vector here, which represents the coefficients, right? These are the four coefficients of the polynomial in coefficient form. Then doing this sort of matrix vector multiplication, that is giving us exactly what we want. It's giving us the vector of evaluations. And you might notice that this matrix here, it definitely looks very structured, right? It's what you might sort of call mathematically structured. It's not just a bunch of random elements. Every single element of this column is a 1. And this column, you're going 1, 2, 3, 4. You're sort of counting up. And in this column, you're going up by squares. And so there's definitely a pattern. Every single element of this matrix follows a pattern. So let's see if we can sort of isolate what that pattern is. One thing that we can do to make the matrix even sort of more structured is to rewrite things in terms of powers of 2. Right? This is something that that we sort of saw last week in Paul's, or 2 weeks ago, I should say, in Paul's presentation about Reed-Solomon codes. That was another situation, and because Reed-Solomon codes are essentially polynomials, that was another situation where it turned out to be mathematically useful to think of things instead of just as numbers in this finite field. We can think of them as powers of 2. And it turns out that all 4 of these numbers, 1, 2, 3, 4, can be rewritten as a power of 2. So maybe the first thing we can do is we can check, how can we rewrite 4 as a power of 2? Does anyone have a sort of conjecture about what power we can raise 2 to get 4? This is maybe too easy of a question.
Mm-hmm.
Yeah, 2. I think I heard 2, and that's right. So we can replace 4 by 2 to the second power, and that gives us basically an equivalent way of writing 4. And now we can write 3. We can rewrite 3 actually as a power of 2 as well. This is maybe a bit harder. And I see a question in chat from Jacob: was 2 chosen to be a generator of the field or for some other reason? And the answer is yes, it was chosen to be a generator of the field. If you sort of recall from last week, Paul, there was a bit of discussion about generators, but the nice thing about 2 is that you can raise it to different powers, and you can get every non-zero element of the field. And I see an answer in chat for the question of 3, and it says that yes, 2 to the third power is actually 3. And that's something you can sort of evaluate in your head. 2 to the third power is 8, and 8 mod 5 is equal to 3. So we can rewrite that. And, we can actually rewrite the 2s and 1s as powers of 2 as well. So I'll just do that there. And now that we have all of this, we can apply a rule to sort of simplify things. If you have 2 to the power 3 to the power 3, that's basically taking an exponent twice is sort of the same thing as multiplying those two exponents, right? 2 to the 3 to the 3 is actually going to be the same as 2 to the 3 times 3. And so if I do that rewriting, I get this matrix, which now has a very sort of, it's a little bit more verbose than what we had before, but it's also a little bit more clear what the sort of structure is here. So now not only is it the case that we have 2 to the 0 down the column, but we also see that we have 2 to the 0 along the top here. And we have 1, 2, 3 here. And we have 2, 4, 6 here in the bottom row. And we have 3, 6, 9 in this sort of middle row here. Now, we notice that the exponents here are very close to being a multiplication table. And this is something I think we noticed in the talk 2 weeks ago as well. And so if only it were the case that these two rows here were switched around, then it would actually be a perfect multiplication table. So I'm going to make one more change, which is to switch those rows around so that we can have that sort of perfectly line up. And that's sort of fine. All I have to do in this sort of matrix multiplication here is I switch these last two rows, I switch around the last two elements of this vector, and I switch around the last two elements of this vector, and everything sort of works out. So what we get here is a matrix, which is a sort of very special matrix. It's known as the DFT matrix, or a DFT matrix. You could think about a DFT matrix for a different generator, right? For example, 3 is also a number which is a generator of this field. And so you could think about 3 to the 0, 3 to the 0, 3 to the 1, 3 to the 4. But all that we see that to solve this sort of coefficient to evaluation problem, essentially all that we're doing is we have to find a very quick way of multiplying this matrix to this vector. And while this would sort of, in general, it would be pretty hard because, this is a pretty big matrix. It's an n squared sized matrix. The fact that it's so structured, right? Basically every element of this matrix is 2 to this sort of multiplication table element. We conjecture and we'll see that perhaps there's actually a faster way of doing this transformation. Before I move on to that, maybe I'll pause for questions again.
I think I have a quick comment about the size of the matrix as it relates to our system. So we see this example of like having 4 columns, but in reality, in RISC Zero's system, the execution traces are powers of 2. So these, to just give people in the audience who might not be familiar an idea, this could be very, very large.
Yeah. So that's that's definitely an important thing to note, is that 4 here is the critical number, but instead of 4, it would really be the number of cycles approximately of whatever program you wanted to execute. And it's also worth noting that instead of F5, right, the field of numbers modulo 5, it would actually be a much bigger field. In fact, much, much bigger, even bigger than the number of cycles, because it's important that you don't randomly get 2 field elements turning out to be the same when they shouldn't be the same. That's sort of a cryptographic important cryptographically important thing. So if there are no real questions about this, I'll move on to sort of the presenting how to do this sort of fast coefficient form to evaluation form trick. And I'll present it in a way that's sort of relevant to the other things that are done in the Fry protocol. But taking inspiration from this, treating the matrix. I mean, essentially what we've done here, I'll go back, is instead of viewing these numbers as numbers 1, 2, 3, 4, we're definitely viewing them as powers of 2, right? So 1 is 2 to the 0, 2 is 2 to the 1, 4 is 2 to the 3, or sorry, 4 is 2 to the 2, and 3 is 2 to the 3. So, basically just taking inspiration from that and seeing that it seems like the correct way of sorting these numbers is to sort them as powers of 2 rather than in the traditional way of going 1, 2, 3, 4. It seems like 1, 2, 4, 3 is a little bit more natural somehow. And so instead of evaluating P of X for some random X or some arbitrary X, let's think about it in terms of evaluating it for X being 2 to the K for some K. And we know that, for any K, we can get any X that we want, basically. So, a good thing to think about when you're trying to design a fast algorithm is what is a good way of breaking the problem down into subproblems, right? This is sort of the so-called divide and conquer method, which is very sort of powerful throughout algorithms. If you ever have to write a fast algorithm, the divide and conquer method is probably going to be the way that you do it. And so we basically need to find a way of the divide and conquer method tells us that if you have a problem, you should try and break it up into similar problems, but of a smaller size. And so what our problem looks like is this polynomial with four components. So how can we break that up into subproblems which consist of solving the same problem, but for polynomials with fewer elements or fewer coefficients? And one way that might occur to you is that maybe we can take the coefficients from P, right? We can take 3, 4, 4, and 1, and we can make new polynomials, smaller polynomials out of those coefficients. And that turns out to be the critical trick. So what I'm actually going to show you all how to do here is to split this polynomial up into basically the even polynomial and the odd polynomial. So here I've taken the x cubed part and the x part. Those are x to an odd power, and I've written them in blue. And then the 4x squared part and the 1 part I've written in red. And if I rearrange this a little bit, I can put the blue terms next to each other and the red terms next to each other. And I can sort of factor out an x. I see that I sort of have, it's really, I have a polynomial here, which is red, and I have another polynomial here, which is blue. And the blue polynomial has half the coefficients that the original polynomial did, and the red polynomial has half the coefficients. So this seems like it could be a good potential way of breaking down the problem. And so let me just define these new polynomials based on what we have here. So I see that I have 3 and 4 as the coefficients to my blue polynomial. So I'll make a new polynomial, and I'll use y instead of x to make it clear that it's a sort of we're operating over x squared here, right? It seems like we're operating over x squared here, but we want a polynomial that's over. If we just want to talk about a polynomial over one variable, we'll talk about it in terms of p of y, which is equal to 3y plus 4. And you could think of y as sort of what's going to stand in for x squared. And similarly, we can have this even polynomial, which is 4y plus 1. And so the central idea is going to be that if we can evaluate these polynomials for all of the powers of 2 to the k squared, right? Because for the original polynomial, we wanted to evaluate it on x equals 2 to the k. For these polynomials, we want to evaluate it on y. And if y is x squared, then we want to evaluate these polynomials on powers of 2 to the k squared. And what we'll show is that if we can do that, then we can basically compute p of x on any power we want. We can solve our original problem. So let's see how that works. This is sort of the most critical part, so I'll pause briefly for questions and see if anyone has anything they want to ask first. Okay, if no one wants to ask anything, I'll go ahead. So we have p to the x. We'll just write that down here. We have our definitions for p odd and p even. And let's say that we have our evaluations for p odd on 2 to the 0 and 2 squared, right? Rather than on all the individual values, we have it on 2 to the 0 and 2 squared. And if we do the math on these, right, we get the values 2 for p to the odd on 2 to the 0 and 1 for p to the odd on 2 squared. And similarly, we can work that out for p even. We can evaluate p even on 2 to the 0 squared and we get 0, and we can evaluate p even on 2 to the 2 squared and we get 2. And I've written these in separate colors so that it'll be sort of easier to see what happens next. How can we now evaluate px on an arbitrary value that we want to evaluate it on? So we can take p of 2 to the 0, and if we substitute 2 to the 0 in, we get this expression here. But we see that we have 2 to the 0 to the 2, and that's really just 2 to the 0. And similarly, 2 to the 0 to the 2 here is just 2 to the 0. So we can replace this 2 to the 0 to the 2 by 2 to the 0, and that gives us this expression. But now we see that the blue here is just this exact evaluation here. And similarly, this red evaluation of 4 times 2 to the 0 plus 1 is exactly this evaluation here of p to the even, or p sub even on 2 to the 0. And so it turns out that just using this purple 2 and this orange 0, that's all the data that we need to evaluate p on 2 to the 0. And it turns out to be 2. Now let's do it for 2 to the 1. Similarly, we have 2 to the 1 squared, and we have 2 to the 1 squared here. And that becomes 2 squared and 2 squared. And we see that those two values are the evaluations of p odd and p even on 2 squared that we computed here. So we have the cyan 1 here and the brown 2 here. And if we substitute those in, we can evaluate p on 2 to the 1, p on 2, which is 4. We can then do the same thing for 2 squared. 2 squared squared is 2 to the 4th. And 2 to the 4th is really just the 0, right? If I take 2 to the 4th, that's 16, and 16 mod 5 is 1. So that's basically the same as 2 to the 0. One sort of trick that you can think of when you're doing field arithmetic or modular arithmetic is that the numbers in the bases, right? You can always add or subtract 5 from those numbers, but for the exponents, you actually add or subtract 4, right? Which is sort of the totient function. That's just one of those sort of vagaries of field arithmetic. So we again get 3 times 2 to the 0 plus 4 and 4 times 2 to the 0 plus 1. These are just the evaluations of the purple 2 and the orange 0. And so we again get an expression that just depends on the orange 2 or sorry, the purple 2 and the orange 0, and we can again evaluate the polynomial for this particular value. And the same thing happens again for 2 cubed. We can basically reduce 2 to the cubed squared to 2 squared. And that gives us, these evaluations of this odd polynomial and this even polynomial. And so basically, in each case, what we get is that, we have here alternating purple and cyan down this column. We have alternating orange and brown down this column. And then we also have an additional multiplicative factor, which is just the input, right? In this case, it's 1, 2. These are just the powers of 2. 1 is 2 to the 0, 2 is 2 to the 1, 4 is 2 squared, and 3 is 2 cubed. And so this is, the sort of basic way in which this is sort of a very, this is only one sort of step of the process, right? You could imagine doing this for a much larger polynomial. And the nice thing about this is, even for a polynomial with potentially millions of coefficients, this process would not take too long, because you only have to do about, like only a couple of million operations in order to evaluate this, right? So, right, P odd, right? So like assuming that we already have P odd on all of these values, right? And we already have P even on all of these values. These sort of, each term in blue here or in red here is already computed. And so all we have to do is, for each evaluation that we want to do, we just have to do one multiplication and then one addition in modular arithmetic. So it turns out to be very fast to do this way. You don't have to do a number of operations which is going up like the square, which is quadratic in the size of basically the problem that you have, which is, you don't want to be multiplying the entire matrix out. You want the faster way of doing it, which is what we have here. And so, yeah, so just to I guess, round out the story on the sort of computational complexity of this problem, we've taken the problem, we've broken it down into 2 sub-problems that are each half of the size. And then we did, an amount of work that was not too much work to combine those answers. And if we had a much larger polynomial, what we could do is we could just keep breaking down the problem, right? We would break the problem into 2 problems of half size, and then each of those would be broken down into problems of quarter size. And then each of those would be broken down into problems of 1/8 the size, and so on. And that would add some overhead. But if you're having the problem at every step, even a very large number, if you keep dividing by 2, you'll very quickly get to 1. And so the fact that we are doing this sort of recursion only really adds a logarithmic factor to the size of the problem. And so we end up doing much faster than multiplying out the matrix. And this is, if you're sort of familiar with big O notation, this is what's known as n log n time. And really, this is sort of almost equivalent in spirit to being able to do something in linear time. So this is definitely a much faster way than the quadratic multiplication, and it's the only thing that makes it possible to do this when you have matrices that are of size 1 million by 1 million. And so that is the number theoretic transform. And I'll just sort of give a very quick explanation of how to go the other way, in fact. And I won't be too serious about all of this. I'll just say that, okay, let's say that we have a bunch of evaluations, and we want to get the the polynomial back. And just to point out, this is sort of what the FFT is most like, I think, because with the FFT, we add a bunch of sine waves, and here we're adding a bunch of monomial terms. We're trying to find a bunch of coefficients for x cubed, for x squared to match the data that we have, basically. So just to remember the matrices, right? This was the matrix equation that we had. And what we really want to do is to invert this matrix, right? So if this matrix is M and we multiply it by this vector to get this result, then to go back from the result to the matrix we started with, we want to multiply by the inverse matrix. We want to do a sort of matrix that's the opposite of what we had before. And so what we need to do is we need to find a way of inverting this large matrix. But it turns out to be very convenient because this matrix has such a clear structure with its sort of multiplication table exponents properties that, in fact, the inverse of the matrix is actually very similar to the matrix itself. So here on the right is actually what the inverse of the matrix on the left is. You basically just replace the 2's by 3's, and then you multiply the whole thing by 4, or really the inverse of 4, but the inverse of 4 is actually 4. And so this is all to say, right? You can check if you want to ensure that each of the, if I were to multiply this matrix by this matrix, I would actually get the sort of identity matrix that doesn't change a vector at all. But the sort of stunning realization is that because these matrices are so similar, I can just apply the same algorithm, but with powers of 3 instead of powers of 2, and that would give me the coefficient out of the evaluations. So it's sort of fascinating that this, Fourier analysis problem, the forward problem is actually the same in some sense as the backward problem. You're just doing it with a slightly different generator. As we mentioned, 2 is one generator of this multiplicative group, but 3 is the inverse of 2. And so I just do the same operation, but with the inverse of the generator, and it gives me back the result. And so that is basically a summary of the discrete Fourier transform. So thanks for coming, and definitely, feel free to ask any questions you may have about all of this. Yeah, it was, great to talk to you all.
Hi.
Hi.
Thank you for your presentation. Very impressive. My question is actually for the last slide, you gave let's say inverse of the first one. I'm wondering how can I come up with 3 and 4? Is that easy to get such number, or I need to any rules or any formula I can use to just simply get the 3 and 4 from the previous matrix?
Right. So yeah. So how do we get 3 here? So yeah, I could have been more clear about this, I think, but the way that we get 3 is that 3 is just the inverse of 2. So 3 is the number that when multiplied by 2 results in 1 in the finite field that we're working with. So how is it possible when you have a finite field to, given a particular element of that field, find another element such that they multiply to 1? To do this, you use you use what's called the Euclidean algorithm. So there's basically an algorithm which says that I have 2 multiplied, but I have 2, and I want to find some coefficient to 2 such that when I have 5 and some coefficient of 5, they sort of multiply together to get 1. And so there's an algorithm for evaluating the inverse of any particular element. in a field, or in at least in a prime field. So that's how you get 3 from 2. And then what is 4 here? 4 is basically just the size of the field here. So how do we get 4? 4, I've written it as 4 here, but you could actually maybe think of it a bit more appropriately as the inverse of 4, or you could think of it as maybe just -1 would be a better way of thinking about it. So the key realization is that, you know, if I multiply, right? So let's say that I was going to multiply a particular row of the matrix on the left and a particular column of the matrix on the right. If it was an off-diagonal row and column, then it would be something like, I would get something like 3 times 2 to the 0 plus 3 times 2 to the 1 plus 3 times 2 squared plus 3 times 2. Or sorry, that would be if I were on diagonal. Sorry, let me amend that statement. If I were to multiply a row, and a column that were so to find the coefficient here, basically the easiest way to think about it maybe is to just remember that the upper left most cell of the identity matrix has to be 1. So if I take a bunch of 1s, right, the top row here is a bunch of 1s, really, and the side column here is actually a bunch of 1s. And so if I just multiply this matrix by this matrix, I'm going to get something that has a 4 in the upper leftmost column, because it's just going to be a sum of 4 different 1s. And so I need to take something which is the inverse of -1, right? The inverse of 4, which is -1. And so 4 here is sort of meant to stand in for -1, which is, you know, in the field with 5 elements, -1 is the same thing as 4.
Okay, I get your point. So another question actually is, when can I apply these rules to matrix? I mean, for general or for some specific situation, I can use this rule.
So yeah, what has to be the case in order to apply this rule? So basically, it has to be a matrix that has this form of all of the columns here are sort of ascending powers of a particular value. So right, in the case here, right, we have, this is known as the DFT matrix, right? The discrete Fourier transform matrix. You can also call it a slightly more general thing to search for is a van der Monde matrix. And so basically the rule is it has to be some element where each column are just increasing powers of that element, where the power always increases by a fixed amount. So, right, if I look at this column, the power goes from 0 to 2 to 4 to 6. And 0, 2, 4, 6, that's a linear progression. And the same thing is true with this last row here. It goes 0, 3, 6, 9, and that's a linear progression. So whenever all of the rows of the matrix are a linear progression that starts at 0, the powers are powers that where the exponent is a linear progression that starts with 0, then it's possible, it will be possible to do a version of this rule that inverts the matrix. And what you'll get is a matrix where all of the columns are that way, right? So the inverse matrix, the columns are always we have a linear progression 0, 1, 2, 3, a linear progression 0, 2, 4, 6. So basically, that's just going to be the general rule.
Oh yeah, I recall that. So yeah, thank you very much.
Yeah, thank you.
So is this method a recent invention, or has it been known for like hundreds of years?
That's a good question. So of course, the sort of use of this technique for the sort of cryptographic process of Starks is pretty new. I mean, that's sort of where my expertise lies. It really came about, I think, in 2018 or so was when the sort of Stark, the research on the Stark paper came out. But it's definitely the case that Fourier analysis and the sort of basic ideas behind these transformations they have a very long history. I think going back even to the 1800s. If you watch the Veritasium video, like I did recently, I think it was around the 70s when the sort of discrete version of the Fourier transform was first sort of realized. They realized that it would be a convenient way, I guess, of doing sort of, seismic analysis. And so that was the first application, is sort of like sensing earthquake waves, I think. And so that was how it started. And basically that was the first time that it that this had been implemented as an algorithm. And I guess since then it's been sort of very useful.
Yeah, thanks.
Yeah. So I guess if there are no more questions, thanks everyone for coming again. We've been recording this meeting, so hopefully we'll put the meeting up as a YouTube video or a series of YouTube videos on our YouTube channel, and probably I'll also make the slides available there as well. So yeah, thank you all for coming.